All right, so get this. Today, we're going to be looking at quantum gravity corrections. Yeah, like what if gravity, the force of gravity, it's not as constant as we think. What if it's got these like little super tiny, almost imperceptible glitches caused by, quantum mechanics? Pretty wild, huh? Well, that's exactly what we're diving into today, this wild world where gravity's got a little bit of a quantum jitter.
Mhm.
So we're going to be looking at the work of this physicist, Sven Fowler. He's got this paper, Effective Field Theory of Gravity, Leading Quantum Gravitational Corrections to Newton's and Coulomb's Law. It's a bit of a dense read, I'm not going to lie, but that's why we're here, to break it down, make it something that we can all, wrap our heads around. So we've all heard of Newton's law of gravity, right? And Coulomb's law of electrostatic force. You know, those classic equations from physics class. They tell us how objects attract or repel each other. But what happens when we bring in quantum mechanics, when we add that weirdness into the mix?
That's the big question. And this paper, it's taking it head on. It's looking at gravity as an effective field theory at low energies. So basically what that means is physicists can make predictions about how gravity behaves, even though we don't have a complete quantum theory of gravity yet.
So it's like we're trying to bake a cake, but we don't know the exact recipe. We might have to, make some adjustments along the way, but we can still end up with something delicious.
Yeah, exactly. It's all about focusing on what we can observe about gravity at the energy levels that we can measure. It's kind of like if you're looking at a painting, like a masterpiece,
Mm.
and you're just examining one brushstroke. You don't need to see the whole painting
Mm-hmm.
to appreciate the detail and skill involved.
Okay, I'm starting to get the picture. So how does this paper, how does it go about calculating these quantum glitches,
Yeah.
these quantum gravity corrections?
Well, they use a technique called the background field method. They basically split the gravitational field into two parts. You've got the classical background, which is what we're all familiar with, and then these tiny quantum fluctuations, which represent the glitches that we're interested in.
So we're separating the signal from the noise. We're trying to listen in on those faint whispers of quantum mechanics influencing the gravitational field.
Exactly. And to do this, they use, you might have heard of them, Feynman diagrams. These diagrams, they visualize particle interactions with all these lines and loops, and they allow physicists to track how these quantum fluctuations affect the overall force.
Feynman diagrams, they're so fascinating to me. But I don't know, I always find them a little bit intimidating too. It's like trying to read a foreign language. Can you decode
Yeah.
some of the key takeaways for us?
Yeah, sure. So the main thing is these diagrams, they help the researchers get to a modified equation for both Newton's and Coulomb's law. And here's where things get really interesting. These modified equations, they include these tiny little corrections due to quantum gravity.
So you're saying those textbook equations, that we all learn, they might not be. The whole story, there's this whole layer of quantum complexity that we need to consider.
Exactly. So let's look at the quantum gravity corrected equation. For Newton's law, it's equation 66 from the paper. It says 5r1 NHER1 plus frac 3g m1 plus me1 plus frac 131 plus 6 in bar 1.
Wow. Okay. That is, that's a lot to take in. I'm definitely going to need you to break that down for me.
Sure, no problem. So the first part, frac ray g m1 plus mb war, that's just your classic Newtonian potential. The second part, with a frac 3g m1 plus meb war, that's a correction from Einstein's general relativity. It comes into play when you have strong gravitational fields.
Okay, so far so good. What about that last part?
The really interesting part is the third term, the frac ray t war. This term represents the quantum gravity correction. It depends on Planck's constant, which is like a fundamental graininess of the universe. At the quantum level,
So wait, hold on. Does that mean the force of gravity between objects could be slightly different at really small distances because of these quantum effects?
that's exactly what it suggests. It's like the fabric of space-time has a subtle fuzziness to it at the quantum level. But there's a catch. These corrections, they're incredibly tiny.
Like, how tiny are we talking?
So to give you an idea, the paper calculates that term, frac me bar, as being equal to $2.1640. That's way too small to measure with our current technology.
So even though we can't observe these corrections yet, directly at least, what makes this so important? Why should we even care about these infinitesimal changes to gravity?
That's a great question. Well, these calculations, they offer us a peek into this world where gravity and quantum mechanics, they intersect. They help us understand the interplay between these two fundamental forces, even if it's really subtle.
Yeah, I see that. It's like we're getting our first glimpse of this hidden world where gravity's dancing to the tune of quantum mechanics.
Exactly. And what's even more fascinating is that the paper looks at how other particles influence these quantum gravity corrections. So particles like photons, which are particles of light, or even these hypothetical particles called massless scalars.
Massless scalars. I gotta admit that's a new one for me.
Think of them like
Oh,
potential
neat.
particles. Like photons, they don't have any mass. They could be.
Yeah.
Exotic particles we haven't discovered yet. Or even something simple, like a theoretical particle called a scalar neutrino.
Okay, so the more particles you add to the equation, the more complex these quantum corrections become.
That's the idea.
Hmm.
The paper actually includes a factor n in the equation
Mhm.
to represent the number of these massless scalar particles. So it shows how the strength of the correction can change based on how many of these particles are around.
My brain's already doing some heavy lifting here. But this is really exciting stuff. So we've got gravity. It might have these tiny quantum glitches, and we can calculate these corrections, even though we can't measure them yet. And other particles, they can influence the strength of these corrections. Anything else we should highlight before we move on?
Yeah, it's important to remember. This paper is mainly focused on the theoretical implications of these findings.
Mhm.
It's not so much about immediate practical applications. It's more about expanding our fundamental understanding of how the universe works. It's like laying the foundation for a whole new area of physics.
Right. It's like saying, hey, we've discovered a new continent, but we've only just stepped onto the shore. There's a whole world to explore here.
Yeah, that's a good way to put it.
Now, we've been talking about Newton's law, but what about Coulomb's law does the research find? Similar quantum corrections to the electrostatic force.
Absolutely. The paper has a modified equation for Coulomb's law, too. It also includes quantum gravity corrections. It's equation 67 in the paper. It says VSQEDRR plus frac 3G M1 plus frac 3G M1 plus frac equal frac M122 plus frac M1E22 plus M22E12 plus M D12E22 plus M22E22 plus M1 and 22.
Whoa. Okay. That equation, it looks even more intimidating than the last one. Can we unpack that one too?
So the first term, VDAR, that's just the corrected Newtonian potential from equation 66. The second term, with the tilde alpha there, is the fine structure constant. And then the remaining terms, those are all your quantum gravity corrections to Coulomb's law.
Okay, so even the electrostatic force, the force between charged particles, it's got these tiny quantum glitches too.
Exactly. Quantum gravity seems to have this influence on both gravity and electromagnetism at their very core. It's intertwining these forces in ways we're only just beginning to understand.
This is, mind-blowing stuff. Before we go any deeper, can you give us a quick recap of the key takeaways from this paper so far?
Sure. So first, remember that idea of effective field theory. It's a really powerful tool that lets physicists study gravity, even without a complete theory of quantum gravity. Second, even though these quantum gravity corrections are really tiny, they offer us some crucial insights into the relationship between gravity and quantum mechanics. They're hinting at this deep connection between these fundamental forces. And lastly, the complexity of these calculations with the Feynman diagrams and all the advanced math. It really shows the level of sophistication that's needed to explore these frontiers of theoretical physics.
It's amazing to see how physicists are pushing the boundaries of what we know. But I'm sure some of our listeners might be wondering, what does all this mean for us? How does understanding these quantum gravity corrections affect our everyday lives?
Yeah, that's a fair question. This research doesn't have any immediate technological applications. But remember, fundamental discoveries, they often pave the way for future innovations.
It's like the discovery of electricity. It took decades before its full potential was realized, and it led to the technologies that we use every day.
Exactly. Understanding the quantum nature of gravity could have similar far-reaching implications in the future. It could lead to new technologies or even whole new branches of science.
It's a really encouraging thought. So, one final question before we wrap up part one.
Yeah.
If we could actually measure these quantum gravity corrections, what would it tell us about the universe?
Well, that's the ultimate question, isn't it?
Oh.
If we could observe these tiny corrections, it would not only confirm our theoretical understanding of quantum gravity, but it might unlock some of the universe's deepest secrets. It could give us clues about the true nature of space-time itself.
What kind of clues are we talking about?
Well, so we see space-time as smooth and continuous. But what if at the tiniest level it isn't? What if it's got this grainy, quantized structure? That would completely change our understanding of reality.
So it's like saying the universe might be pixelated at its most fundamental level.
Precisely. Imagine the possibilities if we could actually see those pixels.
I'm already feeling like I need to take a break to process all this information, but I can't wait to hear more.
Yeah, let's take a short break, and we'll come back for part 2, and we'll delve into the specifics of these fascinating calculations.
Okay, welcome back. I'm still kind of reeling from that idea that space-time might be pixelated. It's wild to think about. What might be hidden at that level?
Yeah, it really is. And I mean, these are the kind of questions that really drive physicists,
Yeah.
to explore these most fundamental laws of the universe.
So in part 1, we talked about how researchers are calculating these quantum gravity corrections to Newton and Coulomb's laws they're using. This idea of effective field theory and these fascinating visual tools called Feynman diagrams. Before we get too deep in the weeds here, can you remind us why Feynman diagrams are so important in this research?
Yeah, absolutely. So Feynman diagrams, they're like this visual language that physicists use to describe and calculate interactions between particles. They're like a roadmap, showing us all the possible ways that particles can interact and exchange energy.
So instead of just looking at equations, physicists can actually see what's happening at the quantum level.
Exactly. So each line in a Feynman diagram represents a particle. And then the points where the lines meet, those are called vertices. And those represent the interactions themselves.
And in this research, the Feynman diagrams are showing how gravitons, which are those hypothetical particles that carry the force of gravity, how they interact with other particles.
That's right. So the paper explores a variety of different Feynman diagrams. Some of them just involve gravitons, and others include photons, which are the particles of light, and then those massless scalar particles that we discussed earlier.
I see. So by analyzing these diagrams, physicists can figure out how all these different particles might be
experiencing the force of gravity at the quantum level. Precisely. It's like putting together a giant jigsaw puzzle. Each Feynman diagram represents a piece of the puzzle. And by carefully analyzing each piece, we can start to see the bigger picture of how gravity works in the quantum world.
The paper mentions that some of these diagrams have loops, which make the calculations like extra tricky. What's the significance of those loops?
Yes, the loops. They represent one of the most mind-boggling aspects of quantum mechanics, virtual particles.
Virtual particles. Okay, you're going to have to explain that one.
So imagine the vacuum of space. We tend to think of it as empty, but according to quantum mechanics, it's actually teeming with activity. Particles are constantly popping in and out of existence, borrowing energy from the vacuum, and then quickly disappearing.
It's like the vacuum is constantly bubbling with these particles.
Yeah.
But they're so fleeting that we can't actually observe them.
Exactly. And these particles, they're called virtual particles. And they're represented by loops in Feynman diagrams. They might be short-lived, but they can still interact with other particles and influence the forces that we observe.
That's incredible. It's like there's this whole hidden world operating beneath the surface of what we can see. This world governed by quantum mechanics.
That's a great way to put it.
Yeah.
And the more loops you have in a Feynman diagram, the more complex those quantum interactions become, which means the calculations get even more challenging.
I can only imagine the amount of brain power and mathematical acrobatics that are required to analyze all those diagrams and calculate those quantum gravity corrections.
Yeah, it's pretty impressive.
Yeah.
But even with all this theoretical work, there's still the question of whether we'll ever be able to actually measure these incredibly tiny corrections.
That's right. I remember the paper's conclusion mentioned it would be practically impossible to verify these results with experiments in the foreseeable future. Did that dampen your enthusiasm for this research at all?
Not at all. I mean, remember, scientific progress often happens in stages. First, we develop our theoretical frameworks. Then we make predictions based on those frameworks. And finally, as technology advances, we can test those predictions experimentally.
So it's like, we're explorers, charting a course to a new land, but we haven't built the ship to get there yet.
That's a perfect analogy. Yeah. So building that ship, in this case, the experimental tools and techniques that are needed to probe these quantum realms, that's a challenge in itself. But it's a challenge that physicists and engineers are actively working on.
That's reassuring. I hate to think all this incredible theoretical work might just be a thought experiment with no way to actually test it.
Right. And remember, I mean, theoretical work lays the groundwork for future discoveries.
Yeah.
Who knows what kind of technological advancements might come along that could allow us to measure these quantum gravity corrections.
It's true. It's like those old maps with "Here be dragons" written in the uncharted territories. Maybe someday those dragons will
But
become familiar landmarks in our understanding of the universe.
exactly. Now, there's one more fascinating aspect of these quantum gravity corrections I want to touch on.
Okay, I'm all ears.
So, this paper, it focuses on the influence of gravitons, photons, and massless scalar particles. But remember, our universe is filled with this diverse cast of characters, all those particles in the standard model, like electrons, quarks, even Higgs boson.
So, could these other particles also be affecting the force of gravity at the quantum level?
That's a great question, and it's a natural next step to consider. So this research provides
A framework.
and a set of tools that could potentially be expanded to study the influence of other particles.
So it's like saying, okay, we figured out how gravitons, photons, and scalar particles affect quantum gravity now. See what happens when we add the rest of the particle zoo
Yes.
into the mix.
Exactly. Each particle has its unique properties
Yeah.
and ways of interacting. Incorporating them into these calculations could reveal even more subtle and fascinating aspects of quantum gravity.
It's incredible to think about the complexity of the universe. At this level, it's like peeling back layers of an onion. And at each layer, we find more intricacies
Yeah.
and mysteries to unravel.
I couldn't agree more. And that's the beauty of science. It's this never-ending journey of discovery. Each answer leads to more questions, and each new insight opens up new avenues of exploration.
This is definitely one of those deep dives that leaves me with more questions than answers, but in a good way. It's exciting to think about what future research might uncover.
I agree. So we've just scratched the surface of this fascinating area of physics in part 3. We'll step back and consider the broader implications of these findings. We'll talk about what this research tells us about the nature of space-time, the search for unified theory of physics, and the future of quantum gravity research.
All right, welcome back to our final deep dive into quantum gravity corrections. You know, we've been on quite the journey so far, exploring these tiny glitches in gravity and electromagnetism that might be caused by, the weirdness of quantum mechanics. We talked about all the tools that physicists are using to investigate these things, like effective field theory and and those super intricate Feynman diagrams. But now I want to get to the big picture. Like, what do these findings actually tell us about, the universe and our place in it?
Yeah, that's the real heart of it all, isn't it? We've been digging into the how, how physicists are actually calculating these corrections. But now it's time to tackle the why. Why is this research so important? What are the bigger implications?
Okay, I'm ready. Lay it on me.
So one of the most profound implications, I think, is that it really strengthens the case for a unified theory of physics. Physicists have been searching for this for a long time, this single elegant framework that could explain all the fundamental forces of nature, gravity, electromagnetism, the strong and weak nuclear forces. And this research, by showing this link between gravity and quantum mechanics, it kind of nudges us closer to that dream.
It's like we've been trying to solve two separate puzzles, one for gravity and one for quantum mechanics. But now we're starting to see they might actually be part of the same bigger puzzle.
Exactly. And finding that connection is a huge step. It suggests that there's this deeper underlying reality that governs both the big world of planets and stars and the tiny world of atoms and particles.
So if we could, crack the code of this unified force, would we finally have that theory of everything that physicists have been searching for? Would we have the complete blueprint of how the universe works?
A theory of everything. Yeah, it's like the holy grail of physics.
Yeah.
It'd be this complete description of reality. But even if we achieve that, there would probably still be mysteries to unravel. The universe is incredibly complex and full of these emergent phenomena that arise from the interplay of simple rules.
Okay, it's like, even if you knew every single rule of chess, you couldn't predict every possible game.
Right.
There's still that element of surprise and creativity and how those rules actually play out.
That's a great analogy. There's definitely a certain level of irreducible complexity
In the universe. But a unified theory would give us that
Yeah.
fundamental framework, like a foundation for understanding everything else.
Speaking of foundations, this research, it also kind of shakes things up in terms of how we understand science. I mean, we usually think of space-time as this smooth, continuous fabric.
Yeah.
But these quantum gravity corrections, these give something different. At
the Planck scale.
the smallest possible unit of distance. Exactly. These corrections are hinting that at these super tiny scales, space-time might not be smooth at all. It could be grainy, quantized. With this structure, we can't even really comprehend yet.
So it's like the universe is pixelated, but at a level so small that, our technology can't even see the pixels? What would a pixelated universe even mean?
That's the question.
Now
That's
that-
driving a lot of research
Right.
in quantum gravity. So if space-time is truly quantized, it would have huge consequences for how we understand black holes, the Big Bang, the very essence of reality.
This is mind-blowing stuff. It makes you realize just how much we still don't know about the universe.
Yeah, and that's what makes it so exciting. Every new discovery opens up new questions, new possibilities. The quest to understand quantum gravity, it's like this journey into the unknown, and each step we take reveals more mysteries, more wonders.
And like those old maps, with "Here be dragons" marking the unexplored territories we're venturing into, uncharted waters here. But who knows what incredible treasures we might find.
Exactly. And what's so cool is this isn't a solitary pursuit. You've got physicists all over the world
Yeah.
who are collaborating,
Yeah.
sharing their knowledge and insights. They're pushing the boundaries of understanding.
Together.
It's this collective effort to unlock the universe's deepest secrets.
Yeah.
And this paper by Sven Fowler, it's a valuable contribution to that effort. It might be focused on the theoretical side, but it gives us this new piece of the puzzle, a new way of looking at how gravity might behave at the quantum level.
Exactly. It's a reminder that even this highly theoretical research, it can have this ripple effect, bring us closer to a deeper understanding of the cosmos
Right.
and our place in it.
As we're reaching the end of our deep dive, are there any final takeaways that you want our listeners
Yeah.
to ponder? Yeah, I'd say. A few key things to keep in mind. The search for a unified theory of physics. It's still one of the greatest challenges in science. And this research provides a really fascinating clue. The nature of space-time. It's more mysterious than we often think. And exploring its quantum properties could lead to some revolutionary changes in how we understand reality. And finally, the journey of scientific discovery. It's a marathon, not a sprint. It takes patience, collaboration, and this relentless pursuit of knowledge.
I like that. Well said. I hope our listeners will walk away from this episode
Mm-hmm.
with a renewed sense of wonder, a deeper appreciation for the complexity of the universe, and maybe even a little spark of inspiration to explore these ideas further on their own. So thank you all for joining us on this deep dive into the world of quantum gravity corrections. It's been a wild ride, and we can't wait to explore more of these fascinating scientific frontiers with you in future episodes.
Thanks for listening, everyone.